So I call this talk Reengineering Natural Kinds, and let me start by sort of explaining the motivation for framing the material this way. One main point I want to stress is that I think scientists are conceptual engineers. And I think they do conceptual engineering routinely and as a matter of professional pride, right? I mean, what scientists do is they create new concepts, they develop new concepts, and if they do that well, they might get a Nobel Prize or whatever they want to get. So it's not a surprise that something that we can recognize as conceptual engineering should be happening in the course of scientific work. So what I'm going to give you today is certainly not a meta-philosophical commentary on conceptual engineering, partly because there are just so much better people to do that than I can. And it's not even going to be a work of conceptual engineering on any philosophical concept. I'm going to talk about how scientists do conceptual engineering on their scientific concepts. So this is intended as a piece of philosophy of science, not as really meta philosophy about philosophical methodology. But I hope it will be interesting enough, even for those of you who are interested in meta philosophy primarily. So my view is that really any good process of inquiry should be prepared to do conceptual engineering, and science is not only not an exception, but it's kind of the prime example of how people do conceptual engineering. And just to be clear, this statement from Stephen Koch is, I think, the best succinct image of what I think of when I think of conceptual engineering. So I'll quote him briefly here from the Phil Papers site that is managed. So he says, instead of asking what our current concepts do mean, conceptual engineers ask what these concepts should mean. Our actual concepts are not necessarily ideal, and that improving them is an important desideratum of philosophy, and I'm adding and of science. So that's the first basic spirit of what I'm trying to do. The second main theme of underlying today's presentation is a naturalistic approach to the whole concept of natural kinds. So what I think of as naturalism here is not the sort of extreme view that philosophical questions should be purely answered by natural science, but recognizing at least a continuity between philosophical and empirical scientific inquiry, and also trying to think of, why are we calling certain things natural kinds? What do we mean by natural? And my answer there is, well, that should at least have something to do with what we learn in natural science. So I've called it in some place practice-based naturalism, right? That when we look at natural kinds, we should regard a classificatory concept as a natural kind if it is sufficiently effective in aiding inquiry in the natural sciences. So it's not, right, it's a pragmatist perspective in that we take seriously a concept that helps our inquiry. It's not so much the view that we should follow the verdict of natural scientific inquiry, right? And there's a kind of underlying humanism in this, the basic position that empirical success is our only access to nature, and that's going to be revealed to us only in human terms. I'm not really today here to argue for humanism. I'm just telling you that that's the perspective I take. And it's a little, well, it's a sharp contrast, right, from this now classic statement in the Stanford Encyclopedia of Philosophy by Alex Bird and Emma Tobin, who say to say that a kind is natural is to say that it corresponds to a grouping or ordering that does not depend on humans. So what I'm thinking of is rather the opposite. And the people I do follow more closely, there are many, but I've just picked out two. There's John Dupre, who says there's certainly no harm in calling a set of objects that are found to have substantial number of shared properties a natural kind. The discovery of such a kind, however, provides no basis for the supposition that some particular properties can non-arbitrarily be singled out as essential. And a similar statement by Stephanie Ruffy, who emphasizes what is epistemically fruitful. So again, broadly speaking, a pragmatist attitude. That's what I'm taking. Again, I'm not here to really extensively argue for this perspective. Rather, what I want to do is give you a set of historical studies taken from this kind of perspective. So I definitely want to get away from the classic metaphor for natural kinds of cutting nature at its joints. Again, I'm not saying this doesn't make sense, but I think that the more productive motto for natural kinds is suck it and see. Now that phrase always mystified me when I was learning English. What are we talking about? Are we trying to be obscene here? No, I'm told that it's about boiled sweets. You don't know what it's going to taste like until you pick one up, suck it, and see. It's interesting that we say see rather than taste, but that's a whole other topic. The third theme that I want to, that's underlying today's presentation is something about the nature of the work of conceptual engineering, which I think really often, very often goes and should go by the mode of development that I've called epistemic iteration in previous publications. So I don't think there'll be time to get into this explicitly. I will do it if there is time, but please know that the idea of epistemic iteration underlies the cases, and you'll be able to see. In case there's absolutely no time for discussing epistemic iteration, here's how I defined it originally. I mean, it's a method of getting on in the absence of any indubitable foundations, right? And I think much of science works according to this method, and some of philosophy as well, if what I think about conceptual engineering is correct, and if conceptual engineering is what we should be doing in philosophy. So I defined epistemic iteration as a process in which successive stages of knowledge, each building on the preceding one, are created in order to enhance the achievement of certain epistemic goals. The main point is that we start our inquiry on some uncertain basis, right? Because that's all we've got. And then we rig up our inquiry so that what we learn from that inquiry can be used in order to correct or refine the starting point that we take. Okay. So I predict that's all the time I'm going to have to say about epistemic iteration, but in the question period, if anyone would like me to expand on it, I can. So I want to talk about, in the remaining time, 4 cases from the history of science in which what we should, I think, regard as natural kinds are shown to be concepts that have really developed in significant ways. And I'm going to see the process of development as conceptual engineering. And there are going to be these 4 examples. The last one, temperature, comes from my book of 2004. The other 3 I've taken from a paper I wrote in this volume, edited by Katie Kendick, who I think I spotted in the audience right now. So thanks for coming, Katie. You'll learn nothing from today's talk, but nice to have you here. I do recommend the whole volume that she edited, Natural Kinds and Classification in Scientific Practice. But I thought I would start with fixed air for a few different reasons. One, that many of you probably have no idea what that is, so that'll be less boring. And because it is actually a Scottish story, since I'm allegedly in St. Andrews. So the term originates from actually England. Stephen Hales in 1728 came up with this term to indicate air, meaning basically any gas that was fixed, held in solid substances. And how do we know that? Well, because by heating or some other process, chemical reactions, this gas can be released, right? So he said it's basically air that has been fixed in a solid substance, and really it meant fixable air, right? Because if this gas could be combined with solid or liquid chemical substance, then that's that kind of air. Because we think, right, ordinary air, like atmospheric air, we don't think it does this, but I mean, we now in chemistry do think it can do it, but you know, back then it wasn't known. So it seemed like a very special kind of gas, right, to Hales, that it could be fixed. And then Joseph Black in Edinburgh made a very particular study, right, of fixed air. So this was his medical dissertation of 1755 at the University of Edinburgh, where he discussed many things, including this thing, magnesia alba, which is, right, something you take for to deal with stomach upsets. And part of what he did was a study with lime, right? So quicklime, which is the solution of calcium hydroxide in modern terms, right? When it's dissolved in water, if you bubble what we now call carbon dioxide, what he identified as Hales's fixed air, if you bubble fixed air through lime water, right, it goes cloudy. And we now say it's because this reaction of CO2 and CaOH2 produces calcium carbonate, which is what we call limescale, right? So Black came up with this lime water test, and that's when this fixed air really entered the realm of serious chemistry, right? So, okay, why am I telling you about this? Because this is a very simple case in which the meaning of a term was deliberately changed in the course of scientific investigation. So Hales had meant a fixed air to be whatever may have been held by a solid chemical substance and released as in the gaseous form. Black made it more specific, right? He said, not any air that will come out of a chemical reaction is fixed air. No, in order to be fixed air, it must pass the lime water test. So the extension of the concept became much more specific. And this is a very routine occurrence, right? As anyone who's been thinking about scientific concepts will know. So now I want to pause that story right there and raise an epistemic question. So, we celebrate Joseph Black as having made first definitive specific criterion for telling when we have fixed air. But how did he do this, right? So he proposed the lime water test because he knew, right? So let me put it in the abstract now. So we're trying to come up with a test for the identification of a substance, right? So is this stuff we have in front of us X, whatever X is? So is this gas fixed there, we ask. And Black proposes this particular test that's based on a regularity, right? This stuff here must be X because it's doing Y, and we know that X always does Y. So this gas must be fixed there because fixed there passes lime water test. But the question is, how did Black know that? It's tightly circular, right? In order to establish that fixed air will make lime water cloudy, you have to first know whether you've got fixed air when you do the test, and it goes into a tight circularity. So how can we learn or even confirm that X always does Y when we don't in the first place know how to identify X? So who gave Joseph Black the idea of the lime water test? Why did they agree that it made any sense? So this is where the iterative thing comes in, right? So initially he was using the old Hale's notion, right, or fixed air as anything that's coming out from a chemical reaction. So that's the more primitive definition. And then, at least under some situations, he learned this interesting fact that the old-fashioned fixed air made lime water cloudy, right? So then he says, there's something more specific going on, and he decides to redefine X as X prime here, right? So fixed air now is whatever makes lime water cloudy, whatever passes the lime water test. And then, yeah, fixed air passes the lime water test, becomes tautologically true. So we've gained a conventional, useful conventional regularity, right, by redefining the concept of fixed air according to the test. And that redefinition in this case came down to a sharp reduction of the extension of the concept. So there's a much longer history, which I'm not going to give you the blow by blow for, but basically how it goes, right? So Black defines it operationally through the lime water test, and then after Lavoisier's work is widely accepted, fixed air is redefined. Fixed air as Black, right, re-engineered it, gets redefined as carbonic oxide, right? And you learn how to synthesize this by burning carbon-containing stuff. And then there's the next step, which is to distinguish CO2 from CO, and so on, right? And at every step of this process, the meaning is changing. And that includes extension or reference. And I think the interesting question, right? So if you give this to the old Kripke style philosopher who worries about reference fixing, they'll say, well, fixed air must have always referred to CO2. People just didn't know it. But I mean, that's plainly untrue, because Hales didn't mean CO2, even if you're just talking about extension. He meant all kinds of other gases that can participate in chemical reactions. No, I think the extension was deliberately changed, as well as the intention. And the question, interesting question to ask, is whether the scientists were wise in making that bit of conceptual engineering. And yes, I think they were wise, because there are clear epistemic gains in this process of engineering. So I think, first of all, what Joseph Black did in making a definite, easy to use, unambiguous in result test for the identification of fixed air was I think worth the change in basic meaning. And then afterwards, in the subsequent steps, you get things like a tight link with Lavoisier's oxygen-based chemistry when we can identify fixed air as an oxide, which not all Hales style old-fashioned fixed air can be, right? And then later on, you get links with Daltonian atomic chemistry, then you get links with carbon-based organic chemistry and physiology of respiration, all that stuff. So, I mean, the irony in this story is that they eventually just junked the term fixed air and called it carbon dioxide, CO2, but the genealogy of the concept is still fixed air, right? Okay, so that's the first case. So let me move on to the second study. This one's for Carolina Pulkin and Eric Sherry and several other people, philosophers of chemistry. So this is the very concept of element, right, which we would regard as a very respectable natural kind term in chemistry. And the gist of this case, which I will cover only superficially, is that the concept of chemical element has really gone through a very interesting long process of conceptual engineering. Now, again, if you know the history or philosophy of chemistry, this will be old news to you. So let me, the concept is ancient, but let's start with Lavoisier, since we already mentioned Lavoisier. And Lavoisier famously, right, advocated the so-called operational concept of chemical element, where we say we apply the term element to express our idea of the last point which analysis, by which he meant decomposition, is capable of reaching. And here again, there's a circularity, right? How do we know whether we've made a decomposition in a chemical reaction if we don't already know which substances are more elemental than which, right? So we'll say, we say, yeah, Lavoisier made the decomposition of water into hydrogen and oxygen. And clearly we say that's a decomposition because we already believe with Lavoisier that oxygen and hydrogen are elements and water isn't. But if we don't already believe that, you can argue it different ways. And some of Lavoisier's opponents did argue that water was still an element and hydrogen and oxygen were compounds that you generate by doing funny things to water, like electrolysis. So Johann Ritter in Germany, for example, said, yeah, what you do in electrolysis is at the positive electrode, you're mixing water, making it combine with positive electricity, and that compound is oxygen. At the negative end, you're making water combine with negative electricity, and that compound is hydrogen. So unless you've already decided what's elementary, Lavoisier's very neat definition isn't actually operationally useful. So again, the actual solution that scientists adopted was this process of epistemic iteration, and this was happening in a process of conceptual engineering that the scientists themselves were carrying out. So let me just very quickly run through the steps of re-engineering that the concept of chemical element went through, right? So, initially, I am not looking back to the ancient Greeks here. I'm looking at something more humble, starting with the alchemists, but the lab-based ones, not the highly mythological people. So there's, in the early days, this presumption that substances that are apparently homogeneous and durable are elements, or they are elementary, right? So water is a good example. Various metals, right? There's no obvious way in which gold can be turned into something else. You can melt it and solidify it again, draw it out and blah, blah, but the basic properties seem to remain. And especially if these substances could withstand harsh operations, then they were considered elementary. So harsh operations like extreme heating or treatment with acids would break down or alter visibly non-elementary substances, but the elements would withstand it. So that's a very, down to earth, on the ground sense of what an element might be. And then with the work of Lavoisier, but even before that, this thing which I called in another place, compositionism comes in. This is a sort of they made the old hands-on element concept metaphysically fancier, right? They went, if not atomic, at least into a picture of some sort of microscopic building blocks, right? Viewing chemical reactions as dissociations and reassociations of these durable building blocks. And again, I mean, this process, I think, is highly iterative because to begin with, they needed some rough and ready notion of what's likely to count as an element, and then they would do more chemical studies on those substances and see if they can make sense of the chemical reactions in terms of this atomistic picture. If you just started by asking what are elements, well, in terms of atoms, there would be no way to get going. And then step 3 with Lavoisier is the emphasis on conservation of weight, right? And at this stage, some things that had been considered chemical elements were eliminated, right? Things like caloric, phlogiston, light, electrical fluid, all of which don't have any weight, right? They were acknowledged not to have weight by their own proponents. So, okay, when we go in with Lavoisier with the emphasis on weight, yeah, we get rid of this whole section of the previous table of elements. And then some ideas of composition were changed, right? So metals used to be considered compounds before Lavoisier, and there were elements and so on. So refinements going on. And I mean, at each step, if you want in the question period, right, I can go back to each step and talk about what epistemic advantages there were in making these specific changes. Some are obvious, some are not. So, oh, I went back, sorry. So then the next stage, right, is the age of real chemical atomism with Dalton and others, where you get ideas of definite and invariable weight ratios, first between the macroscopic combinations and then between atoms, right? So we finally arrive at the notion of atomic weight by which chemical elements are defined. And as Eric can tell you better than anybody, that shift into the more subtle modern definition of chemical element according to atomic number rather than the gross weight, right? Atomic number being the number of protons in the nucleus of an element. So again, something very, very fundamental, something that the defenders of the non-human based idea of natural kind would really favor. That notion of element also has this long history of conceptual engineering, and yeah, my perspective is we regard these things as natural kinds, not because we're convinced that they reveal some unchangeable order of nature, but because they help us in our investigations in natural science. So let me go to another example, which is probably something you don't think about every day, but you should, right? It's the notion of acid or acidity. And, this is something we are living with every single day. If you don't think so, just think about your stomach acid, and without which we're nothing. So, of course, acids are one of the earliest chemical classes recognized as such. I'm gonna start by giving you this little bit from John Stuart Mill. There's a curious little bit of the system of logic where he pulls out this historical example. He was curiously well informed about chemistry, and I don't know the full story of why that was. So he cites the fluctuations in the theoretical concept of acid as, quote, a striking instance illustrating the general point that since the classifications in any science are continually modified as scientific knowledge advances, the definitions in the sciences are also constantly varying. So I think if you could resurrect Mill and put him in this seminar, I think he'd be entirely happy with the notion of conceptual engineering. So sorry, I keep going back because I won't bore you with why. So the steps in the re-engineering of the concept of acidity go like this. So first, the almost ancient concept is stuff that's sour, right? Mostly food, lemons, oranges, various other things you find naturally occurring. So, as soon as people were able to make vinegar, I think this concept was born. Right? I had a fun moment in the early days of looking into this, looking for, right, what's the chemical essence of vinegar? It's acetic acid, right? What's the etymology of acetic? It's vinegar. So acetic vinegar is made of vinegary acid. That's it. That tells you the origin of this very concept in the prehistory of chemistry. And then starting with that, this is a story initially of, well, it's a twofold story going to stage two. One is the realization that there are other kinds of acids, those that you should never eat. The so-called mineral acids of the alchemist, so things like sulfuric acid, hydrochloric acid, nitric acid. And then the discovery that acids not only taste sour and corrode things, but they do interesting things chemically, like changing the color of litmus and other indicators, and that they neutralize alkalis, which are harsh in their own ways, right? So the knowledge base is definitely growing, and the concept of acid, right? I mean, they really had to quickly depart the sour stuff concept and come up with something more theoretically enriched and interesting. And then stage three went in the more metaphysical direction, when many chemists try to find, well, if there are different kinds of acids, there must be the essence of acidity. And many theories were proposed for this, including Lavoisier's infamous idea that oxygen was the essence of acidity, right? I mean, many of you know very well that that's how Lavoisier coined the very word oxygen as the generator of oxy, meaning sharp, acidic. So stage 3, right? So now I give you the first glimpse of a failed stage of conceptual engineering. I mean, the epistemic gain that people would have got if this had succeeded is obvious, right? You would have gained the unified theory with all the trimmings that come with that, but it just didn't work, right? So stage 3, basically given up, and then I'm cutting a very long story short here. About 100 years later, you get the theory by Svante Arrhenius in Sweden, which says that acidity is the effect of hydrogen ions in watery solutions, right? And along with that come the pH, right, which is a measure of the concentration of H plus ions in water, and the creation of the pH meter, which is a whole other story, right? Those of you who've used pH meters probably know the feeling, I don't really know how this thing works, but it seems to work. It's got a mysterious glass electrode. I can talk about that if you want in the question period. But stage 4 is a really major development, right? I mean, you would almost think that just at the theoretical level, stage 4 acid concept has almost nothing to do with stage 2 concept on the surface of it, but part of Arrhenius's wonderful work was making the link, right, about how it is that this concept of acid can make sense of the neutralization of acids and alkalis and all that. But that only arrived with his brand new ionic theory, right? Identifying H plus and OH minus in water. And then in the next step, right, you have a rather straightforward development of this. That's a generalizing step by Brønsted in Denmark and Laurie in England, saying it's not just H plus ions in aqueous settings, but any substance that can donate H plus to other substances can be considered. Acids and alkalis are acceptors of H plus, not necessarily containing OH minus. So that's a generalizing step that's quite straightforward. And the next stage, which is quite complex, which I won't go into full detail now, is the work of the American chemist G.N. Lewis, who changed the notion of a donor of H plus to an acceptor of a lone pair of electrons. And this is significant because it's a very serious theoretical departure, right? And also it cut the connection with the pH measure, right? The pH meter picks up, right, in a subtle way, the concentration of hydrogen ions in a solution. It doesn't pick up the accepting of a lone pair of electrons thing. So here we have what I think of as a fracture of the concept. And we could think about the philosophical implications of that. So that's the summary of the re-engineering of the acidity concept, which is a long and fascinating history. Now, that's William Thomson, Lord Kelvin. I had to bring another Scottish person in for today, but it's not hard to do if you're looking at the history of the physical sciences. So, Lord Kelvin, that's about the right picture. That's Kelvin as a youngster. I don't know how old he was in that picture, but because I'm going to talk about his invention, I'll freely say, of the concept of absolute temperature, which he did at age 24 in 1848. So I think that's about right, that picture. At age 24, he had already been for 2 years the professor of natural philosophy at Glasgow University, a position which he held for 53 years until he finally retired. I won't tell you all the personal story about Kelvin, but I'm presenting him today as a conceptual engineer. And we all know that he was a serious engineer as well as a physicist, right? His early claim to fame was having solved some tricky technical problems about the laying of the cross-Atlantic telegraph cable. So he had certainly a lot of engineering credibility, but I'm going to say he was a wonderful conceptual engineer too. So the first conceptual engineering move he made, and this is concerning temperature, was to take the concept of temperature from being something very concrete to something very abstract. And the phrase absolute temperature, that means abstract temperature. It doesn't necessarily mean having the absolute zero. And I'll come back to that in a moment. So 1848, this is what Kelvin said. Although we have thus a strict principle for constructing a definite system for the estimation of temperature, yet as reference is essentially made to a specific body as the standard thermometric substance, we cannot consider that we have arrived at an absolute scale. Now, what he's talking about is paying at the same time homage and critique to the work of Victor Regnault in France, who had mentored him. Regnault was, I mean, by consent, the greatest experimental physicist in all of Europe at this time. One part of his work was, right, so Regnault had a commission from the French government to gather all relevant data to the workings of the steam engine. So there are 3 enormously fat volumes of the French Academy, right? 3 entire volumes were taken up by Regnault's report, and he did really painstaking empirical work, part of which was to establish what thermometers were good to use. And Regnault's conclusion was to get as far away from theory as possible, because none of the theories were trustworthy or testable without first having a good thermometer. So he said, right, I'm going to make types of thermometers that were empirically usable by virtue of being self-consistent, right? So that's a long story, which I tell in my Inventing Temperature book. But anyway, so Regnault by the 1840s had established that the thing to use was gas thermometers. And air, just normal atmospheric air, never mind that it's a mixture of 2 different gases. Air was the best thing to use, just empirically. So Kelvin had been drilled in experimental physics in Regnault's lab. That was part of the program of training young Kelvin to be the Glasgow professor anyway. So he had enormous admiration for Regnault, but he also said, it's not good enough for us fundamental theoretical physicists, because it says reference in the definition of temperature is made essentially to a specific body, namely air, as the standard thermometric substance. So he's saying, look, temperature is one of the most fundamental concepts in physical theory, and we want to tie the very meaning of that to a particular substance that's not even an element. I mean, that really offended his sensibility as a theoretician. So he said, this goes on, we can only regard in strictness the scale actually adopted in practical thermometry as an arbitrary series of numbered points of reference, sufficiently close, good enough for the requirements of practical thermometry. So how did he propose to go beyond it? He said, we have to go to the completely abstract theory, which can serve as a conceptual foundation for the definition of temperature. And for that, he went to the fledgling version of thermodynamics, right? I mean, Kelvin was one of the people who created classical thermodynamics, right? He started by rediscovering Sadi Carnot's work, the Carnot cycle that we've all suffered from if we've done physics. And he liked Carnot's theory because it was completely abstract. It makes no, right? This kind of phenomenological thermodynamics makes no reference to any substances in its fundamental theory, and then it can be applied to particular ideal heat engines, right? Whether it be an air engine or steam water engine. And so this is what Kelvin does. The relation between motive power and heat, as established by Carnot, is such that quantities of heat and intervals of temperature are involved as the sole elements in the expression for the amount of mechanical effect to be obtained through the agency of heat. So Carnot's theory gave you, right, formulas for correlating how much heat passed through the cycle and how much mechanical work was produced, right? And Kelvin said, aha, because the amount of mechanical work produced is not only the function of the amount of heat passing through the engine, but the temperature difference between the hot cycle and the cold cycle in the Carnot scheme, that we can use that functional relationship to define temperature, right? So that's what he did, right? He said, this is the initial definition of absolute temperature he gave in 1848. A unit of heat descending from body A at the temperature T of this scale to a body B at the temperature T-1 would give out the same mechanical effect in a Carnot engine, whatever the number T, wherever you are on the scale. That's it, right? As promised, no mention whatsoever of a concrete substance. And I'm going to take a pause here and you know, just marvel at what a daring step of conceptual engineering this was, right? Here's a age-old concept, temperature, that had been developing quite slowly, right? That the first 2 chapters of my book are about that slow process of, you know, that too is conceptual engineering, taking it from an Aristotelian quality to, right, an operationalized quantity measured by thermometers. And Kelvin says, well, we don't want to do that anymore. That's just not good enough. That's okay for practical people, but we have to create a theoretical concept. And again, we can debate later why he felt compelled to do that. Well, what's the epistemic advantage of creating such a stunningly abstract concept? And so then comes the very long story of what happens from 1848 onward. I want to just point out 2 features of the rest of the story, and I can tell you more if you're interested in the questions. One thing I want to tell you is that, right, so some of you who don't already know this story will still have noticed there's something weird about this definition, right? It says a unit of heat descending from a body A at temperature T to a body B at temperature T at -1 gives out same mechanical effect. No, I mean, what we now say is an amount of heat is converted into mechanical work. That's energy conservation, but 1848, he doesn't have that yet, right? Energy conservation is just coming in. He hadn't yet been convinced by James Joule to adopt energy conservation. So he's working with the original Carnot theory in which energy is not conserved. Heat instead does work in falling from high temperature to low, just like in a water wheel, water might turn the wheel and do work, right? So then, as a consequence, something that happens is after he goes over to new thermodynamics based on energy conservation, he also had to change the definition of absolute temperature, which he did. And that was another piece of conceptual engineering. And then it created a situation in which he actually had two true notions of absolute temperature, which he had to choose between. And there's right. So this is where the zero thing comes in. The first one had no zero, went to negative infinity. The second one had a zero. And that, you could argue, was one of the epistemic affordances of the second definition. But you could also say, what the hell is wrong with having temperature go to negative infinity? So you can argue about the advantages and disadvantages of that. So that's one point. Kelvin, within himself, he was such a good conceptual engineer. Personally, he made two concepts of absolute temperature, and he had fun choosing between the two. The other thing I want to point out is, having made such completely abstract definitions, how do you measure such a thing? Because actual measurement involves knowing about, right? Actual measurement has to involve concrete, specific substances and mechanisms and so on. So having taken the concept completely away from anything directly observable, let's say, how do you then connect it back to the concrete specific substances so you can measure it? And that's the long story I'm not going to tell you, but it's a whole other story of epistemic iteration, in which he actually starts with the practical notion of temperature and puts that together, right? So he actually takes his Joule's mercury thermometer to give you initial measurements of temperature, knowing that that's not quite right. And then he uses Joule's measurements to assess, right, how much actual thermometers must deviate from the ideal. So he does this through the very tricky experiment called the Joule-Thomson experiment, right? The cooling of a gas as it comes through a very small hole. So how much cooling happens was theorized to be correlated to how much the gas deviates from the ideal. And that means, right, you can tell how much gas thermometers deviate from ideal absolute thermometers. Anyway, I won't tell you that whole story now, but the point is that that was also a piece of conceptual engineering, right? Having made the very abstract one, how do we develop that concept further so it can also be measured? And this is the kind of thing that I think conceptual engineers should and do worry about. So let me just, right, conclude with a few thoughts. One, as I started with, I think scientists are conceptual engineers par excellence. If that's not convincing after hearing these historical stories, then I don't know what will convince you. But I can tell you, right, everywhere you look in the history of science, there is conceptual engineering going on. And then I want to say, right, I started out by giving you a naturalist perspective on natural kinds. How I want to make the same point is that natural kind terms are subject to conceptual engineering just as much as any other terms, I think. So at least in that sort of functional way, there is no difference between what's natural kind and what's not. Now, I think we could and should attach the honorific description of natural kinds to terms that really help us in natural science, but that I'm sure will be controversial. And then looking back at philosophy, I think we could ask, right, I mean, is conceptual engineering a particularly philosophical project? And my own intuition is that it's not, but I want to pose it as an open question. So is there something distinct about conceptual engineering when it's done by philosophers for philosophical purposes? Or is there just a kind of continuum of what I think is right to call conceptual engineering that's done by any intelligent and creative users of concepts. So let me finish there, and thank you all for your attention.